Okay, sorry about the delay, yeah. So let me just start right away. So basically, these 3 lectures will be based on some lecture notes, which you can download from the internet. So basically, you have to go on Google and put my name, and then the first page should be my web page, and there you find a link where you can download these lecture notes. And so in these following 3 lectures, I will go through these notes, mostly writing on the blackboard, but I also need the screen here to show some of the pictures and also the outline. So the topic of my lectures will be topological band crossing. So basically all these semi-metallic materials, what's important there is the band crossing. So in various semi-metals where we have a twofold degeneracy between 2 bands. And so if one wants to classify these topological semi-metals, one needs to study the stability of band crossings. So that's what I want to do in these lecture notes, and I will focus on 2 different types of band crossings. The first type is so-called accidental band crossings, where the symmetries lead to a protection of the band crossing, but the symmetries are not strong enough to enforce this band crossing. And I want to give somehow a pedestrian way to derive a classification of these accidental band crossings. And this will lead us to this 10-fold way classification of topological semi-metals. And then in the second part of the lecture, so starting second part of tomorrow and on Thursday, I then want to focus on this second type of band crossing, so symmetry-enforced band crossings, where you have very strong constraints from symmetry, and they're so strong that they lead to a symmetry-enforced band crossing, right? So you can then make these statements, given a certain space groups, you must have always a band crossing along a certain high symmetry line or along a high certain symmetry plane. And again, I want to classify these band crossings, not fully, but for some space groups, in particular hexagonal space groups. And for both types of band crossings, I want to focus on a few classic examples and discuss what leads to the protection, what is the topological invariant that leads to the protection, and what are the physical consequences of it. Okay, so let me then start with basically chapter 1, these accidental band crossings. And okay, so before I do that, I just want to make some preliminary remarks. So basically, what we're interested in, we want to solve this clock equation. We want to study the situation where we have okay. Okay, so yeah, so you solve this these eigenvalues of this Bloch Hamiltonian, and you want to know what are the, under which conditions can you have a band degeneracies. So that means where you have the energies of 2 bands, M and M prime, are equal at a certain point in the Brillouin zone. So what are the symmetry requirements that you can have such a stable degeneracy? What are the topological requirements that you can have such a stable degeneracy? And so in my talk, I mean, this kind of equation is very general, right? But in my talk, I will focus mostly on this case where this describes electronic band structure in solids. But this type of equation basically arises whenever you have quasi-particles. So one could do this analysis not just for electrons in solids, but also for other types of quasi-particles. For example, in a superconductor, you have Bogoliubov-Duchenne quasi-particles, and you can get a very similar equation, a Bogoliubov-Duchenne equation in this form, and you can study band crossings of these Bogoliubov-Duchenne quasi-particles. But this is even more broader, right? You could also consider phonons, which are a type of quasi-particles, and then study band crossings between phonon bands, or in a magnet, you might have magnons or spinons that also define a band structure in the Brillouin zone, and then you can ask the question under which condition can we have protected crossings between these magnon bands, right? So this is kind of a very general scheme, and it applies to all kinds of different quasi-particles which we can have in condensed matter physics. And yeah, so basically then the first type of band crossing is this accidental band crossing. Okay. And so this basically happens if you have an electron-like and a hole-like band which overlap like this. And so in the absence of any symmetries, you would have here this phenomenon of band hybridization. You would have an avoided crossing and a small gap opens up here. But as you see, if you have certain symmetries or certain topological properties, then you can have a protected crossing where there's no gap opening here. And so that's typical in this accidental band crossing. And so other typical features you have in this accidental band crossing is number one, you have these symmetric symmetries that protect it, so protected by symmetric symmetries. So this would be, for example, point group symmetries such as reflection or rotation symmetries. Then another property you have for this accidental band crossing is that they are protected by a local topological charge. So if you have such a band crossing, then you can define an invariant which will give you this local topological charge. And this invariant will be defined in terms of a line integral or a contour integral with this contour C over some kind of curvature function. So this could be the Berry curvature, but it could also be the winding number density or some other kind of density that you integrate over. And this contour is chosen such that it encloses here this band crossing point. And so then for these accidental band crossings, you find that you'll get a quantized number for these invariants. So meaning that this leads to a protection, right? So you cannot change a quantized number, an integer number, by a small perturbation. So this leads to the projection of these band crossings. Okay, then the third property of this accidental band crossing is that they are only perturbatively stable. So that means you can consider in the system small local deformations in momentum space, which will move here this band crossing around a little bit. So this band crossing will be stable against such small perturbative deformations, but the band crossing, this accidental band crossing, is unstable if you consider a large deformation. So for example, you can consider pulling here this whole band and electron-like band apart, and then you will get a situation where these two band crossings disappear. So this is this mechanism of pair annihilation. And because of this third property, also this classification is only tells you something about the possibility of having such crossings, but the classification of these accidental band crossing don't tell you that such a crossing must be there. It only tells you if it's there, it will be protected. Okay. So now we want to use some kind of pedestrian or heuristic way to classify these types of band crossings. And for that, we are going to use the so-called matrix, Dirac matrix Hamiltonian method. Okay, so this is basically section 2A now. Okay, so we want to classify now these accidental band crossings. Using this so-called Dirac matrix approach. And so basically the idea here is if you look at the physics very close to such a band crossing, you see that the bands basically disperse linearly, so you can approximate your band crossing in terms of a Dirac Hamiltonian. Just locally, just focusing on one single band crossing point. So this has then this form here. It's a sum over the momenta. multiplied by some gamma matrices or Dirac matrices. So that's why it's called the Dirac Hamiltonian approach. Right, so we have, if we are in d dimensions, we have d momenta, and we need to use d gamma matrices to build our Hamiltonian. So these gamma matrices are basically generalized Pauli matrices of given rank, and they form a Clifford algebra representation. So they obey this anti-commutation relation like this, just like the Pauli matrices. And okay, so then if you have this Hamiltonian, basically if you square this, you see immediately you get this energy dispersion close to this bands crossing, right? So it's symmetric, and it's kind of the sum of the squares of the momenta. So you see this simple Hamiltonian describes such a band crossing where you have linear dispersion of two bands crossing each other, one with positive velocity, one with negative velocity at this band crossing point. Yes?
Maybe a general question, but in 3 dimensions everything's fine, right? But once you go above 3 dimensions, more gamma matrices will come from anti-commutation relations for the most general case.
Right, this is very general, right? If you are in 3 dimension and if there are no extra symmetries, then you just use the 3 Pauli matrices here, right? This will be one example. But it's much more general. You know, you can have arbitrary dimension, and if you have symmetry constraints, then also you are somehow constrained which gamma matrix you can use here.
Let's take the 4x4 gamma matrices. The most general Hamiltonian has 16 parameters, right?
Right, I mean, okay, so if the rank is 2, you have the 3 Pauli matrices, and then if you go one step up, you have 5 Dirac matrices, and so on. And then there will be more and more, right? Yeah. I will come to that, how do you have to choose this. Yeah? This will become clear once I talk about the symmetries. Yeah, so basically, I mean, the basic idea here is now you have written down this Dirac Hamiltonian, and you want to know whether this is stable. So basically, this means you want to know whether you can add now a gap opening term to your Hamiltonian. So what does this mean, a gap opening term? It means you would have to be able to add another gamma matrix to your system. So the question you want to ask is it possible to add a mass term? Okay, so this would be another gamma matrix, M gamma 0, for example, which would have to respect to symmetries. If you can add this to your Hamiltonian, this means you will gap out here this band crossing, because then the energy spectrum becomes like this. It's again plus minus, but here now you have the sum of the momenta, and then you have the mass squared, right? Something like this. Okay, so then you see you will never have now a crossing of this positive or negative band, and that means your band crossing is actually unstable. So that's the basic idea. And so to make this a bit more concrete, we have to do the following steps now in sequence for a given set of symmetries. And you have to do this classification with respect to a certain set of criterion. Right? So first of all, the symmetries will influence this classification, because the symmetries will tell you which gamma matrices are allowed, are symmetric or not. Okay, so the classification will depend on the symmetries. And these can be so-called spatial symmetries, which relate different lattice positions to each other. For example, a reflection symmetry or a rotation symmetry, but there could also be non-spatial symmetries which act locally in position space. So this would be, for example, a time reversal symmetry or a particle hole symmetry. So this classification must clearly depend on this. Secondly, it must also depend on the dimensionality of your system and also the dimensionality of your band crossing, right? So you can have a point crossing, or you could have a line crossing, or you could have a two-dimensional crossing. So this also must somehow enter, and it turns out what really matters is not both of these dimensions, but only their difference. So this is the codimension of the band crossing. So this is the difference of the dimension of the system minus the dimension of your band crossing. And finally, what matters here is then also not just the symmetry of your Hamiltonian, but also how your band crossing itself transforms onto the symmetries. Mm-hmm. And this is particularly important if you consider these non-spatial symmetries, right? So they act locally in real space, but in momentum space, they typically relate momentum k with momentum minus k. So if you have a band crossing at a given momentum k, then your symmetry might relate this band crossing to another one at a different point. Or it could be that your band crossing is at the high symmetry point of the Brillouin zone, for example, the gamma point, and then the band crossing will be invariant by itself under the under this non-spatial symmetry. Okay, so let me say a bit more now about these symmetries. We want to classify both in terms of these spatial and non-spatial symmetries. So I have to now think about how these symmetries act on my Dirac Hamiltonian, how they constrain the form of my Dirac Hamiltonian. So this is chapter 3A1, symmetry operations. Okay, and then I would now focus first on the non-spatial symmetries. And basically, there are only three different types one can consider. So this is the time reversal symmetry and the particle hole symmetry, which are both anti-unitary symmetries. So time reversal symmetry constrains your Hamiltonian like this. So it relates the Hamiltonian at minus k up to this similarity transformation to the Hamiltonian at plus k. And it's an anti-unitary symmetry, so that means this tau contains a complex conjugation operator. So it can be written as a unitary symmetry times a complex conjugation operator. That's the constraint on your Hamiltonian, and that will also now then be the constraint on your gamma matrices here. And secondly, if one studies superconductors, one can consider this particle hole symmetry with the operator C. And this is also anti-unitary, so it can be written as a product of a unitary operator UC times the complex conjugation operator kappa. And so both of these symmetries come in two different variants. This basically follows from Schur's lemma. So basically, you can show that this time reversal operator either has to square to plus 1 or minus 1. So this distinguishes the case of systems with and without spin-orbit coupling. If we look at Bloch electrons, more generally distinguish the case between half integer and integer spin systems. And also this particle hole operator can either square to plus 1 or minus 1. This can be interpreted as being a spin singlet or spin triplet superconductor. And then one can also consider this so-called chiral symmetry, which is basically a unitary operator which anticommutes with your Hamiltonian. Okay, so this was basically these non-spatial symmetries. So, and one can now tabulate these different cases. So this leads to these Altland-Zirnbauer classes. Maybe Professor Altland already mentioned this in his lecture. So you basically see here in the last three columns of this table, you see these symmetries. And listed is here now all the different combinations of these three symmetries, right? So we have time reversal symmetry, particle hole symmetry, and this sublattice or chiral symmetry. And the 0 means that the symmetry is absent, and they have a plus or minus, it means that the symmetry is present, and it squares either to +1 or -1. So if one only considers these symmetries, one has already 10 classes one has to consider. But we want to go even beyond that, and we also want to include spatial symmetries, so reflection symmetry as an example, as they also lead to the constraint of your Dirac Hamiltonian. Yeah, okay, so let me just stay with this maybe quickly, right? So basically you have these symmetry constraints now, and I have already erased the Dirac Hamiltonian. It was here. So if you apply these symmetry constraints on your Dirac Hamiltonian, then you find that these gamma matrices must satisfy certain conditions. So these gamma matrices, which are in the kinetic term of your Hamiltonian, have to anti-commute with the time reversal operator, and they have to commute with the particle hole operator if this symmetry is present, and so on. And the mass term, if it exists, has to commute with the time reversal operator and anti-commute with the particle hole operator, and so on. So this is just applying these symmetry constraints on your Dirac Hamiltonian, then you find these conditions, and this somehow enters now in the construction of your Hamiltonian, right? You want to write down at the beginning a low energy model which satisfies the symmetry. So if you have time reversal symmetry, you can only take these gamma matrices which satisfy these equations. Similarly, then if you want to add the mass term, you have to make sure that this is satisfied. And we have similar constraints then also for the reflection symmetry. Right, so reflection symmetry is a spatial symmetry. It relates different points in real space with each other. So for example, we can consider this reflection R, which sends the x coordinate to the coordinate -x. So this is basically a reflection about the YZ plane if we are in a three-dimensional geometry. And if you have this, then your Bloch Hamiltonian must satisfy the following condition. So the Hamiltonian at crystal momentum -k1 has to be equal to the Hamiltonian at momentum +k1 up to this similarity transformation here, yeah? Where U can be chosen to be a unitary matrix like this. And again, we can apply this to our Dirac Hamiltonian where we get some conditions for the gamma matrices. So as an aside here, one should also note that this reflection operator also transforms the spin. So this will become important later in the lecture when we talk about systems with spin-orbit coupling. So it leaves the x component of the spin invariant, but transforms the y and z components of the spin, so sends them to -1. I mean, this just follows basically because the spin arises due to some, you can imagine that the spin arises due to some circulating currents, and then if you think about how these currents get mapped onto their mirror image, you'll find this condition here. So that means if we have a system with spin, then this R must contain a spin component which is I sigma x, right? So this is just the spin operator Sx, Sy, Sc. So to get such a relation here, the spin component of R, you must choose it I sigma x. But of course, R will be in general more complicated because your Bloch Hamiltonian describes maybe a system with many different orbitals and many different atoms in the unit cell. So you will have this part certainly there, but in general it will be more complicated So R is just some unitary matrix which then depends on the particular example how it looks like. But in any case, this doesn't really matter for this Dirac Hamiltonian analysis, but only what matters is now these conditions on the gamma matrices. So we apply this condition here on the Dirac Hamiltonian, and then we find that this first gamma matrix, gamma 1, which is multiplied with the first coordinate kx, has to anti-commute with R, and the other gamma matrices have to commute with R, and also the mass term, obviously, if it exists, has to commute with R. Okay, so these are basically these conditions now on this Dirac Hamiltonian, and now we are somehow ready to make a recipe for this classification, right? So the first step we have done already, namely this is just writing down a Dirac Hamiltonian which satisfies the symmetries that we want to consider. Okay, so basically we can now define a recipe for the classification. Okay, so basically step 0 will be you choose a set of symmetries. And then step 1, this I've already discussed a little bit, is now write down a d-dimensional Hamiltonian, d-dimensional Dirac Hamiltonian that respects these symmetries. And for that, you have to use these relations here, right? So, yeah. And then, so here one has to also now make a remark regarding this dimensionality of the gamma matrices. There was a question earlier on that. Namely, of course, these gamma matrices exist with many different ranks, right? So Pauli matrices would have rank 2, but there are also higher dimensional gamma matrices, which are 4x4 matrices, for example, the Dirac matrices, or 8x8 matrices, and so on and so forth. So which one should you choose? And what you should choose is you should choose the matrix dimension to be minimal, should be minimal. So this means it should be large enough such that you can implement all these symmetries in a non-trivial way, but it should not be any bigger than that, right? So if you want to consider the Weyl semi-metal, for example, then the minimal dimension will be 2x2, so it's just Pauli matrices, because this is enough to implement the symmetries. In that case, you have no symmetries, and you have 3 dimensions, so you just need 3 Pauli matrices. This would be enough. Okay, then step 2 is now you have to think about, can I actually add now to my Hamiltonian a mass matrix? Okay, so check whether there exists a mass term. So M gamma 0, and this gamma 0 has to also satisfy the symmetries, so it must satisfy these conditions that I've written down before. Okay, so you check whether this is possible, and so there are 2 different answers, right? The answer could be yes, it is possible. Okay, so if yes, what does this mean? Okay, it means you can gap out your band crossing, so it means the band crossing is unstable, so therefore not topological. So then you're basically done already, and you can then enter one first result in this table here, and this will be denoted in this table by this entry 0, right? So this means for this minimal Dirac Hamiltonian that you have written down with this given set of symmetries, there is a mass term, so this means this is unstable.
Sorry?
Yes?
If you consider the case of graphene, for example, you can open the gap, but you have this topological invariant by just looking around to get the bare phase of pi in graphene.
Right, so in graphene you will need inversion symmetry with squares 2 plus 1 plus a reflection symmetry. You need the time reversal symmetry with squares 2 plus 1 plus either reflection symmetry or inversion symmetry. If you have these symmetries present, then you cannot add a mass term. And then this also leads to the quantization of the Berry phase. So only in the presence of reflection or inversion, the Berry phase is quantized. Okay. And the other option is, okay, no, there is no such mass term. Then means it is topological. And this is denoted in this table either by a C or a C2. So C means there is an integer number of these band crossings which is stable. C2 means that there is only one crossing stable. As you have two crossings or even number of crossings, you can always gap them out. So you have to do a third step now in this analysis to distinguish between the C and the C2. So to determine whether multiple crossings are possible, so one needs to consider now doubled versions or multiple copyings of the Dirac Hamiltonian. Doubled Dirac Hamiltonians. And you can double your Dirac Hamiltonians in many different ways. So one has to consider all possible doubled versions of your Dirac Hamiltonian. And this is this equation 2.11. So we get the doubled Dirac Hamiltonian, where we basically go to higher dimensional matrices by forming these tensor products, right? So we have these kinetic terms, gamma times k, and we tensor product this with sigma c, or you could also tensor product this with sigma 0. Sigma 0 or just the 2 by 2 identity matrix. And now you can choose here in many different ways which momenta you're going to put here in this first sum and which momenta you're going to put here in the second sum. So this gives the possibility to have many different doubled versions. So intuitively speaking, this corresponds to the fact if you have, for example, a chiral topological state, you can add them with the same chirality, or you can subtract them from each other with opposite chirality. So this would be reflected then in this fact here, where you have, if you subtract the two chiralities, you have the sigma c. If you would add two versions with the same chirality, you would have the sigma 0. So you have to consider both cases. And then basically you go back to step 2, namely you ask then, is there a mass term for this doubled version of the Hamiltonian? And if there is, then it's a C2 classification. If there isn't, then it's a C classification. I mean, actually, you'd have to double again and then show again that there's nothing. But yeah, this is, of course, a bit a longer procedure, but you can do this in terms of induction. Is there any questions so far? Yes?
So one question, is there a reason why you consider only sigma b and sigma 0 in the double version and not sigma x and y?
Yeah, so this is somehow physically, I can say this just corresponds, you add two copies with the same chirality, or you add two copies with opposite chiralities, right? This is the only two possibilities you have. You could argue in a different way. You could just say, I'm just going to use now a higher dimensional representation of my Clifford algebra and somehow rewrite my Hamiltonian now with higher matrix dimension, and then I'll do the same game as before, but now with bigger matrix dimension. And then you would just use here all matrices that appear in this higher dimensional representation. This would be maybe, yeah, like a mathematician would probably do it like that. Yeah. But I think this method gives the same results. yeah, okay, so then I would just now explain this in concrete terms by looking at a few examples, how this recipe works. Right, so the simplest thing we can do is just we go to this class A where we don't have any symmetries at all. I mean, there it's almost trivial, basically. Okay, so I want to start off with this class A, no symmetries, here as you see in this table. And I want to look at the point crossing in 2 dimensions, right? So 2 dimensions, and the dimensionality of my crossing should be 0, so this means P is equals 2. Okay, so then first step, I have to write down a Hamiltonian that describes such a band crossing. So basically, I need 2 gamma matrices for the kinetic term because I am 2 dimension. So therefore, the matrix dimension must be minimum 2 by 2, so I can use the Pauli matrices. Like this, right? So this will be a Hamiltonian with the right symmetries. And now, step 2, I ask myself, is there a mass matrix? Of course, there is a mass matrix. Namely, it's sigma c, opens a gap, and then basically I find that this case is classified by 0. So I can go in my table and put this there. So this would correspond here to this column. Okay, so this row, which is class A, and basically look here now at point crossings. I mean, here it doesn't really matter whether it's at high symmetry or off high symmetry, but I need to look at P equals 2, right? For example, here P equals 2, here we have a 0, here P equals 2, we have also a 0, right? It's consistent, and this is very trivial first example. And obviously, I can extend this now to 3 dimension, where we have the Weyl semi-metal. Right, so it's basically just the same as before, but now we need a third Pauli matrix to write the kinetic term. And now, because I have used all 3 Pauli matrices, I know there is no mass term. So I know immediately this has to be topological. But I don't know whether it's C or C2. So to find out whether it's C or C2, I have to do this doubling now, right? So I have to go to 4 by 4 matrices, and I can consider different versions of this, right? So different ways how you double this. So basically, you have 5 gamma matrices of dimension 4 that 4 are available, and you can choose now any 3 out of these 5 to form your kinetic term. So one choice would be this, where I have the sigma x tensor product with sigma z, and I have sigma y tensor product with sigma 0, and I have sigma c again tensor product with sigma 0. Right, so this is this construction here. Now I have chosen to be kx in this first sum, and the other 2 should be in the second sum. So this is just one choice for this doubling, and I have to ask, is there a mass term? And indeed, there is a mass term. For example, sigma x tensor product sigma x. So this is a matrix which anti-commutes with this kinetic term, and it respects the symmetries because there are no symmetries, and therefore it's a gap opening term, and I know, okay, so this doubled version cannot be topological, so I still don't know whether it's a C or C2 classification, But now I have to consider these other options here for forming these sums. So for example, I could choose it differently, put all k terms in the second sum. So I just basically have this doubling with a sigma 0. Right, so basically it's just this Hamiltonian AH3D tensor product sigma 0. So that means I add one copy with chirality plus, for example, with another copy of chirality plus, and then I'll find that there is no mass term. Okay, so basically I have to consider all possible tensor products of sigma I with sigma j, and then check whether they anticommute with this doubled Hamiltonian. And I'll find that this is not possible. So that means this is also stable, indicating that I have a C classification. So I can go there in the table, and again I see for if I have P equals 3 now, for this very same metal I have this C here, and also here, right? It's consistent. So let's make this a bit more interesting by adding some symmetries.
Can I ask, how do you conclude that it's a classification for this?
It's just, it's not a proof, right? So you basically have to consider more and more copies and show that you can always not add a mass term, yeah.
And also, for adding the mass term, I mean, in principle, you can always add a polymatrix to open up the gap, right? So do you always have to take the tensor product with sigma 0, or is it not as easy as I think it's going to be?
Yeah, so in this case, it's always the one with sigma 0 that cannot be gapped out, yeah. But, I mean, you might have a more complicated situation, so in general, you have to check everything, yeah.
Okay, but the polymatrix is always this way, right?
Where in this example, I mean, this is so simple because we have no symmetries, right? Yeah. Yes.
I'm sorry, but really I didn't get what information you got from just multiplying with sigma 0. I mean, it's just the same like tensor product. The same thing for me.
Yeah, but the difference is now, right, so this would not anti-commute. Yeah, so this choice for a mass term is not a valid choice anymore because it doesn't anti-commute with this Hamiltonian here.
But you chose this mass term that for this version you said that it's random. I mean, you could have chosen other combinations.
Yeah, you have to choose all possible combinations and check for all combinations whether you can add such a mass term, yeah.
And you concluded that mass term from this Hamiltonian.
Yeah, okay, so, okay, let me just state it more clearly. You have to choose all possible doubled versions and then check for all of them whether you can add a mass term. If there is one version where you cannot add a mass term, it means that that the classification is bigger than just C2. Because you have now constructed an example of a system with two such band crossings, which is actually stable. Yeah, so that's the recipe, right? So you have to consider all possible doubled versions of your Hamiltonian. For each of them, you have to check whether there is a mass term. If you find one possible doubled version where there is no mass term, it means you have now found an example of two band crossing which is stable. So then the classification cannot be C2, it has to be higher.
I don't think how it is special to gapless system apart from the fact that you use the Dirac equation, because that seems the same to me that you bring two quantum edge states together, then you see that you can uncouple them, so you get the Z classification. Is it the same, for example?
Right.
Is it
Right.
the same kind of stuff? Or?
Exactly, yeah. But you could have, you can add two edge states which propagate in the same direction that cannot, or you could have two edge states which propagate in opposite directions, right? So in one case you can open a gap, in the other you cannot. Yeah.
That's exactly the sigma 0 and sigma 0.
Right. Okay, I mean, this is really kind of a heuristic approach, but it's ultimately related to this Clifford algebra extension, which puts this on a much more rigorous grounding. But I think in this lecture, it's probably better to have an easier approach than introducing Clifford algebra extensions. Okay, so let me just do maybe one more example where we're going to add a symmetry now. So the simplest symmetry we can add is is reflection symmetry. Okay, this will be example 3. So we have this class A plus the reflection symmetry. And we start again with point nodes in 2 dimensions. So the codimension is then 2. And so we have 2 momenta. So I have to use 2 Pauli matrices or 2 gamma matrices to write down a kinetic term. And now I have to make sure that I can implement here this reflection symmetry. So I need now another gamma matrix to write this reflection symmetry. So for example, if I consider this reflection which lets x to minus x, then I can implement this with the Pauli matrix sigma y. So you can then check that my Dirac Hamiltonian satisfies this symmetry. So this is the defining symmetry of the reflection symmetry. Right, so basically I have here this first part, kx goes to minus kx under this symmetry. And so then if I commute this sigma y through, I get here an additional minus sign from the anti-commutation of sigma x with sigma y. But this is cancelled by this minus sign here. So this is fine. And here this commutes, sigma y commutes with sigma y obviously. So this term is also symmetric under this reflection symmetry. So basically I have done step 1 now. In my classification scheme I have found a Dirac Hamiltonian which satisfies the symmetries. And now comes step 2. So I ask, is there a mass term? So basically here I see I have already used sigma x, sigma y, so I could use sigma c as a possible mass term. But I have to check now whether this breaks reflection or not. So I have to check this relation, r minus 1 sigma c r. So because r is sigma y, this gives me minus sigma c. So therefore, reflection symmetry is broken by the mass term. So it means I cannot find any mass term that satisfies all symmetries. So this is stable. Huh? So band crossing is topological and it's protected by reflection symmetry. Okay, so then I know, okay, it's either a C or C2 classification, so then I have to do again this doubling. Okay, so I have to consider all possible doubled versions. And check whether you can add a mass term or not. If I find one doubled version where I cannot find a mass term, I can conclude that the classification is higher than just C2. And yeah, so this is this choice that you have to do. You tensor product with sigma 0, and you find that there's no mass term that could open up a gap. So for example, you could add sigma c tensor product sigma x. So this would anti-commute with this kinetic term, but it actually breaks reflection symmetry, because if I apply this reflection symmetry, so the reflection symmetry now comes tensor product with sigma 0, then I find that this is broken, right? It does not commute. Okay, this is angular. Okay, so therefore I conclude the classification is higher than C2, and actually it's C in this case. If you go to higher matrix dimensions, you'll find that it is C. Okay, so I think I have just time for one more example, where now I'm going to add a non-spatial symmetry. So I want to consider this class A2. Again, in 2 dimension with a 0-dimensional Fermi surface. So a point node, so Px equals 2. So this class A2, if I go in this table, what does it mean? It means I have no particle Hall symmetry, I have no chiral symmetry, but I have this time reversal symmetry, which squares to -1, right? Yes, it should be this line here, huh? Squares to -1. Okay, so now I have to write again a kinetic term, and I have to use another gamma matrix to implement this time reversal symmetry. So it's basically the same story as before. I have just kx and ky. I can choose here sigma x and sigma y, and then I can implement tau like this, I sigma y kappa. So this is complex conjugation. So basically, right, so this time reversal symmetry will let kx to minus kx and ky to minus ky, and then have to multiply here from the left and from the right with this operator. So basically, I see here, because of this kappa here, I get the minus sign here from this complex conjugation, and here I also get the minus sign because sigma x and sigma y anti-commute. So this clearly is symmetric, time reversal symmetric with this tau, and this tau, so this time reversal operator t also squares to -1. If I just square this, you can see this. Okay, so I've done step 1, found my Hamiltonian. Now, again, the question about the mass term. So I have to check whether sigma c is symmetric under this time reversal symmetry or not. So is there a gap? Is there a mass term? M sigma c would be a candidate. So basically I have to apply here this operator. And now I see, okay, it anti-commutes here. Yeah, okay, we have to work this out, so you will see that this breaks time reversal symmetry. Okay, so that means we have a topological band crossing. So it's either C or C2, and then again you have to do this this doubled version. So basically I can write all possible doubled copies in this form, where I just write here my original Hamiltonian, and then here I have this part which has either plus or minus in front of it. So this lower part in this doubled Hamiltonian is just here. This term is all possible combinations here of pluses and minus ones. Huh? So this is just basically because you can either tensor product with sigma 0 or sigma c. And now you have to check for all of these doubled versions whether there is a mass term. This requires some work. Maybe leave this as a homework. And you find that all these doubled versions actually allow for a time reversal symmetric mass term. Okay, all doubled versions have a mass term. So that means the classification is C2. And this is maybe clear because you have heard already about the three-dimensional topological insulator, and this Hamiltonian describes namely precisely the surface of a three-dimensional topological insulator where you have this Dirac cone, and this is stable because of this time universal symmetry. And we know this, we have the C2 classification for the 3D TI. And you can again check now in the table whether this agrees or not. So basically, we are here at the high symmetry position, P is equals 3, and P is equals 2 actually. Yeah. So here, A2, P2, we have the C2 here. Okay, with this I stop, and then next lecture I would continue with this a little bit, focusing on these band crossings which are away from high symmetry points, and then I want to discuss more these symmetry enforced band crossings where the non-symmetric symmetries are important.
Questions?
You always write down AX sigma X and AY sigma Y. Is there anything that prevents me from AY sigma X, AX sigma Y? Does that change anything?
No, you're free to choose the gamma matrices as you like. Yeah. Doesn't change anything.